we would now like to look at error estimates for alternating series. So we're going to look at the infinite sum. So S is going to be the sum from k equals 1 to infinity of -1 to the k plus 1, a sub k. And that's going to be our infinite sum. And we would like to approximate that infinite sum by a sequence of partial sums. So we're going to look at the nth partial sum and use that to approximate S. And we want to see how big the error is. So again, what is the error in this case? We'll call the error maybe E sub n. And that is going to be the difference between S and S sub n. Now, when we looked at error using the integral test, we just wrote S minus S sub n because we had sequences of positive terms, and so that meant that S sub n was going to be less than S. But in this case, we're not sure whether the partial sum will be larger or smaller than the exact sum. So we're going to look at the error as the absolute value of S minus S sub n. So to figure out how large that is, we're going to consider two cases. Okay, so the first case is when n, our term, is even. So we looked at alternating series before, and we saw that when n is even, that our sum, S, was less than, say, the n plus first partial sum. And so that means that S minus S sub n is less than S sub n plus 1 minus S sub n. But the n plus first partial sum minus the nth partial sum, that's actually the n plus first term. And so here we can see that S minus S sub n is less than a sub n plus 1, the n plus first term. Okay, here we should note that in this case, when n is even, okay, the n plus first partial term is going to be positive. Now, when n is odd, we also know from our earlier work that our sum S is actually going to be bigger than the n plus first partial sum. And so in that case, S minus S sub n is going to be bigger than S sub n plus 1 minus S sub n. And again, S sub n plus 1 minus S sub n, that is going to be a sub n plus 1, the n plus first term. And so in this case, we can put these two inequalities together, and we can see that the absolute value of S minus S sub n must therefore be less than a sub n plus 1, the n plus first term in our series. So here, essentially, right, we're looking at this inequality and that inequality, and when we combine them, that's how we end up with the absolute values. Okay, so this actually gives us our error estimate. It says how large is the error for an alternating series? Well, if we approximate S by S sub n, then the error is no larger than the n plus first term in the series. So let's look at a couple of examples of how we can estimate a series using the first n terms. So first, we're going to decide whether these series converge or not. And then if the series does converge, we're going to use 10 terms to estimate the sum. And then we're going to give an upper bound for the error. So we have this first alternating series. negative 1 to the n plus 1 times n over n plus 1. So we need to check to see if it converges. Since it's alternating, we can just look at the limit of the terms and see if that goes to 0. But the limit of at least the positive part of the terms, n over n plus 1, is equal to 1, which is not 0. So that tells me that the series diverges. Now let's look at this second sum. It's negative 1 to the n plus 1 over n times n plus 1. Again, we're going to look at the terms in the series because they're alternating. We're going to see if the terms are going to 0. So we're going to look at the limit as n goes to infinity of n times n plus 1. And that does equal 0, so that tells me that the series converges. Since the series does converge, then it does make sense in this case to see what the 10th partial sum is and see if that's a good estimate for the infinite sum. So we're going to sum up the first 10 terms. I'm not going to show all of the work for that, but if you do that, you get 0.3821779. And then we want to know how close is that sum to the actual value of the infinite sum. So what is the error for the 10th term? Well, in fact, that error we know is less than the 11th term in the sum. And the 11th term in the sum is going to be 1 over 11 times 12. And if we estimate that, that's going to be 0.007576. So we have that our estimate of the sum is 0.382179. Okay, and then the error is no bigger than 0.007576. Okay, so that tells me essentially, and I'm just going to write this kind of roughly, that our sum is somewhere between 0.3 maybe ish, okay, if we're adding 0.007 or subtracting 0.007, right? And maybe, sorry, not 0.3, 0.37, let's do a little subtraction there, maybe 4, just to be safe. And then it's no larger than, say, 0.39 if I add the 0.007 to my sum. Okay, so that gives us a range of values there for our infinite sum. And so we have it at least to one decimal place with just 10 terms.